Hello everybody. Here's a video I'm making to show you what the chi-square goodness of fit test is today. This will be a very comprehensive video. This is tailor-made for students who are taking the IB course, particularly the IB AISL course. But I'm also certain that if you're doing the AIHL course, this would be a very insightful video for you to understand how the chi-square goodness of fit test works, and um, I will also show you examples where how you could apply this concept onto it, and I will also show you how to use the TI-84. Obviously there are many other calculators that can get the job done, but just particularly I would just show you with the TI-84 just because my class is basically doing the TI-84 calculators. So if you would like to see how this is done with other calculators, just please let me know as well. So before we actually plunge into the goodness of fit test, we'll be looking at a test that you probably would have done it before, which is the chi-square test of independence. They are correlated, and I'll show you what's the difference between the chi-square test of independence and the chi-square goodness of fit test in a short while. Now, before we do that, let's do a quick starter activity just to show us if you could remember the chi-square test of independence. Okay, so let's look at this example here. It says that Tony wants to carry out a chi-square test to determine whether a person's choice of one of the three professions, engineering, medicine, or law, is influenced by the person's sex, gender. So we're going to write the null hypothesis, okay, for this one. So if you remember this, the null hypothesis is we always assume that the two variables, which is the choice of profession and the gender. So we'll be looking at people. Should write person's choice of professions and gender are independent of each other. Okay, so in other words, it means that we're trying to find out whether if you're male, does it affect the choice of your profession, or if you're a female, does it affect your choice of profession? Are they independent? That's always the null hypothesis that we assume. And of course, if we ask for the alternative hypothesis, we're assuming that both of these variables would be dependent of each other, right? And we're also looking at what is the number of degrees of freedom. So in this case, we do know that when it comes to degrees of freedom, we're looking at obviously there is a formula for this, which is looking at the number of rows and the number of columns if we have a table that shows the data. But in this case, if we look at this, because there isn't a table given to us and we don't need to draw a table for this, but we know that a person's choice has three options here, which is engineering, medicine, or law. So what we'll do is we'll take the professions in this case, which is three options here. So I'm just going to call the number of professions to be P, and I'm going to subtract 1, right? Because basically what is a degree of freedom is basically the number of independent pieces of information, right? So if you know how many people take engineering and medicine, then obviously I don't need to give you the data on how many takes law, because you would have easily found out by adding up the number of people taking engineering and medicine and subtract that from the total number of people who takes the survey. So in this case, if I know the number of people taking engineering or medicine, automatically we know the number of people taking law in this case. It's the same thing for gender. If you know how many males take a certain profession, then automatically I don't need to give you the data for the females, because you can subtract the number of males from the total number of people taking the survey. So in this case, I'm just going to multiply that by the gender. Let's just call this G in this case, and I'm going to subtract 1, and we'll multiply these two together. So it'll be 3 minus 1 multiplied by the number of genders. Obviously, it could be a male or female. So in this case, the degrees of freedom would be 2. And usually we denote the degrees of freedom to be df, which is a notation that we use for degrees of freedom. Sometimes they use v, which is fine as well, but I prefer degrees of freedom to be used as df. Now, let's look at the next example here. It says that of the 400 people Tony interviewed, 220 were male, 180 were female. 80 of the people has chosen engineering as a profession. So what we're trying to find out is calculate the expected number of female engineers. All right. So basically, we're trying to find out with probability what are the expected number of female engineers in this case. Now, we do know that in the chi-square test of independence, we always assume that the two variables are independent of each other. So it's the same thing that we could apply to this question. So again, let's look at what the question is really asking, which is female engineers. So we want to find out what is the probability that out of the 400 people that Tony interviewed, that this 180 were female. So we know that we have 180 females here, and we know that we have 400 people who are being interviewed. So the probability of having a female would be 180 over 400. So that's pretty straightforward. Now, then we're going to be looking at the number of people that has chosen engineering. And it says that we have 80 people who has chosen engineering as a profession. So we know that this is 80 over 400. Now, since we assume that both are independent, and we want to find out what's the probability that it's going to be the person who is being interviewed is a female and chose engineering, we're going to take 180 over 400 times 80 over 400 here. Okay, and we're going to multiply this. Now this is the probability that a person that has been chosen would be a female and would also take engineering at the same time. Okay, but we're not looking for the probability in this case. We're looking more specifically the expected number of female engineers in this case. So we should be getting a number and not just simply the probability in this case. So since we have the probability, all right, what we're going to do is we're going to multiply the probability of having a female and who chose engineering, and we will multiply this by 400 because we have 400 people who are being interviewed in this case. So by multiplying this by 400 to the probability that I just mentioned earlier, and if you put this onto the calculator, you will be getting this to be 36 expected number of female engineers. Okay, so just to summarize, we will find the probability of a person who's going to be female and who takes engineering. So we multiply the two probabilities because that's the concept of what independent events are, right? Because the probability should be very low for someone who's going to be female and someone who's going to be choosing engineering. So we multiply the probabilities up together. But since we're trying to find out of these 400, how many people are actually female and who chose engineering, so we have to multiply the probability by the total number of people who are being interviewed. Right, so technically you'll be looking at about 36 people who's going to be female and who's going to choose engineering in this case. And finally, let's look at the next part of the question. It says that Tony would use a 5% level of significance for his test and obtain a p-value for 0.0634. So in this case, you don't even need to use a calculator because they have given you what the p-value is. Now, just to recall your memories here, if we know that if the p-value is less than the significance level, we will reject the null hypothesis, which is basically the two variables that I mentioned earlier would be independent of each other. So let's look at the p-value. That's 0.0634, and we know that that has to be bigger than 0.05, right? So in this case, since we have the p-value to be bigger than the significance level, So in this case, we're not going to reject the null hypothesis. Okay? In fact, we're going to be saying that we will fail to reject the null hypothesis. Okay? And that simply means that if we conclude this, we could easily say that a person's choice of profession and gender would be independent of each other. Okay? Independent. Okay, so here's a quick review of the chi-square test of independence, and I'm going to introduce what the chi-square goodness of fit test will look like. Right, it's more like an introductory video, so I'll probably make another video that gives you a little more details about what chi-square test of goodness of fit test can do as well. Okay, so hopefully this makes some sense. So we're going to start looking at what a goodness of fit test will look like. Now, typically the concept of the chi-square is very similar for both the independence and for the goodness of fit test. What we're looking at is we're looking at a certain type of data, which is the categorical data, and we are looking at specifically whether the differences between the observed data, so this is data that you have, and what you would expect. Usually we'll be looking at from probability concepts. Can we merge these two numbers together, assuming that the null hypothesis is true? Okay, I'll show you how to formulate the null hypothesis, because it's a bit different for a goodness of fit test, because for an independent test we are always looking at whether the two variables are independent or not. But I'll show you in a short while. The null hypothesis will look slightly different because the context of the question is a little different. Okay, so we'll move on to the next part. So a quick recap again. We don't necessarily have to look at the p-value and the significance level. We know that from a chi-square test of independent, if the chi-square test statistic is bigger than the critical value, because the critical value basically is the threshold of you rejecting the null hypothesis. So if your chi-square test statistic is greater than the critical value, you will reject null hypothesis, which is basically this little portion here. Okay, and of course if the chi-square test statistic is smaller than the critical value, all right, in this case we don't really say accept the null hypothesis, we always say fail to reject the null hypothesis, okay, because of insufficient evidence for that. So we're looking at goodness of fit test today. Is really what we're trying to look at is we're looking at how close the observed data fits with the expected data. Now, the good thing about goodness of fit test is that it doesn't have to be simply testing for independence. Let's just put it this way. The chi-square test of independence is a subset of the chi-square test goodness of fit test. So basically, the chi-square goodness of fit test is a bigger test, and the chi-square test of independent is just one of the elements of the goodness of fit test. So obviously I specifically taught the chi-square test of independence first because I felt like it will make a little more sense for you guys. But today we're going to be looking at how the goodness of fit test would generally look like, and typically the concepts work quite similar to the test of independence. Okay, and of course it could, when I say that you could use it for any distribution, and we have learned in this course in the AISL, we have learned how that we have learned distribution like the normal distribution, and we have also learned the binomial distribution. So in other words, we can actually use the goodness of fit test in a normal distribution and also in the binomial distribution as well. But today that's not the focus of my video, but we will come to that in the next upcoming video as well that I will make. Now, okay, we'll talk about the degrees of freedom shortly. Okay, so typically I would like you to take this down as well when you listen to this video, is to know that when we do a goodness of fit test, you basically would make a hypothesis to determine whether the observed frequency, which is the data that you have collected, will be different from the expected frequency. Okay, which is basically, if we work out using probability concepts, what are the expected numbers, or and we're trying to see if there's a difference between the observed and the expected frequency. Okay, the data, which is observed frequency, will usually count how many individuals from a sample for each category. I know this is kind of vague, but I'll show you with a couple of examples later. Okay, I'll probably skip this for now. And the chi-square goodness of fit test, again, we only use just as what we do with the chi-square test of independence. Typically, we look at categorical data, which is, for instance, data that can be categorized. So like gender, that can be categorized into males or females, colors, the type of colors that you like. So again, that can be categorized. Shapes, or even numbers for a dice roll, that could all be categorized in a way. So these are some examples here, but it's not an exhaustive list. So I did mention here, we're looking specifically at the categorical data. So some examples that I added on to the categorical data, like your eye color, are you registered to vote, and so on. Okay, so we're looking specifically at this particular element or a certain type of data that we could only use for goodness of fit test. So we're not looking at discrete, we're not looking at continuous, we're looking at specifically categorical data. All right, so we can't just basically use any data to perform the chi-square goodness of fit test. Now, I thought it would be a good way to start off an introduction to this test by using the rock, paper, scissors, just to give you an illustration of how this test actually works. I think we all know how to play rock, paper, scissors. So the rules of the game is that we know that the paper will beat the rock is going to beat the scissors, and of course the scissors beats the paper. All right, and of course you can have, if you have someone beside you, you can actually play the game as well. Now let's assume that this was the observed frequency, which is the observed data. This is the data that you have collected when you play many games in this case. Now let's look at how many rocks, paper, and scissors we have here. Now we got 66 rocks, we have 39 papers, and of course we have 14 scissors in this case. Now, so obviously it's not equally distributed in a way, but this is actually what we're trying to do with the goodness of fit test. We are trying to test whether all these categories, would it be equally likely? Would it mean that whether this game is actually going to be a fair game, that the choices that's made by the players are equally distributed? That's what we're trying to find out in this particular set of data that's been given to us. All right. Now, I think before we actually talk about how this works, let's look at how many games have been played in this particular question here. Now, we do know that if you have 66 rocks, 39 papers, 14 scissors that's played between two players, I really want to know like how many games that these two players actually play. So let's take 66 plus 39 plus 14. If we add this up, you should get this to be 119. Okay, so that would be 119 games that's been played between two players, and it seems like there were more rocks that came out in the game in this case. Now, so but the thing is, we are not really looking at we want to know that if this game is actually a fair game, because we know that in this particular game, to win in the rock, paper, scissors, there is a 1/3 chance of you winning the game. That makes sense, right? Because you only have either rock, paper, scissors, so you have a 1 out of 3 chance of actually winning the game. Now, if this was the observed data, now what about the expected data that we expect? If this was a fair game, and we're expecting a 1/3 chance of winning the game, wouldn't you expect this game to be done in a more fair way, which means that if I were to take this number, which is 119 games, and I divide this by 3, right? So we approximately should be getting about 39.7 wins for each rock, paper, and scissors. Now, of course, we're not going to get a nice whole number, but approximately we're looking at about between 39 to 40 of each of the outcomes here. So the expected outcomes we're looking would be about 39.7 rocks, 39.7 paper, 39.7 scissors. So it's approximately about 40 rocks, 40 papers, 40 scissors. That's what we're expecting in terms of the data that should be happening if the game was actually a fair game, because it should be an equal chance of you winning. So we're going to test that, and that's really what we are trying to do with the goodness of fit test, is to compare between the observed data and the expected data in this case. So that's what we're going to be performing, and we're going to formulate some hypothesis to show whether this works. Again, we're doing it the same old fashion. We're going to compare that to a level of significance. We're going to looking at p-values or maybe the critical values to see whether this game is going to be a fair game or not. Okay, so this is another way of actually doing the chi-square test, goodness of fit test. All right, now I got a lot of obviously a lot of information here, but I do really want to just spend more time. I'll come to all this later, because this is just literally a summary of the goodness of fit test, and I'm just going to skip all this for now. I'll probably come back to this, and I'll show you how to formulate the hypothesis test shortly. Okay, so let's try to get this out first. Yeah, I'm going to keep my annotations, and I just want to show you a specific example here. Okay, there we go. Now this was a question that was being taken from the Oxford textbook, but I thought this would be a great example to show you how this works. What I'll do as well is to show you how to formulate the null hypothesis and the alternative hypothesis. Again, we're trying to compare the observed frequency with the expected frequency. Remember, we're not testing for independence, because that's not what the goodness of fit test does. The goodness of fit basically does is that we're trying to compare whether the observed frequency and if there is any misalignment with the expected frequency, and that's what the goodness of fit test actually does. So let's look at this. It says that the students in year 8 are asked what day of the week their birthdays are on this year. The table showed the results in this case. So again, we have 12 students here who have birthdays on Sundays, 14 who have birthdays on Tuesday, 17 for Wednesday, 15 for Thursday and Friday, 15 for Friday, and of course 14 for Saturday in this case. So we are trying to find out, write down the table of expected values given that each day is equally likely. Okay, so what we're trying to do is, if this was the expected data and it tells you in the question that it should be that every day should have an equal number of students having the same birthdays, then we need to find out on Sunday to Saturday how many students would have birthdays from Sunday to Saturday, assuming that there should be equal number of students. Okay, because that's what the question is asking. So we're trying to find out if this number differ from the data that's been given to us, which is obviously that the number of students having birthdays on each of the days is different. So if we create a table of the expected value from what the question is basically asking, so I'll draw a little table first. So I'm going to have day, and I'm going to have frequency in this case. So we have Sunday, we have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and of course we have Sunday. Now, first we want to know like how many students are being surveyed in this question. So we have 12 14, 18, 17, 15, 15, and 14. So it will make sense for us to add up these numbers here. Plus 17, plus 15, plus 15, plus 14 here. Okay, so if we add up all these numbers, you should be getting this to be 105 students who are being surveyed about their birthdays. Now, since we're looking at, no, this is not right. If we add up the numbers, we should be getting 1, 4, 5, 6, 7, 1, 2, oh, sorry. It shouldn't be a Sunday here. It should be just from Sunday to Saturday. So 105, this obviously looks correct. So what I'm going to do is I'm going to take 105, divide by 7, because we got 7 days in a week. So that's going to give us 15. So what we're expecting is that there should be 15 students who should have birthdays from Sunday to Saturday, because it says that each day is equally likely in this case. So we're going to perform a goodness of fit test in part B, and what we're going to do is we're going to formulate the null hypothesis and the alternative hypothesis. Now, what we're trying to show here is that the null hypothesis is that we always take the information about what is expected in the question, and it says that each day is equally likely. So we could say that in this case that the data follows a uniform distribution. It's just a very fancy way of writing that the number of birthdays will be the same for each day here. But generally, it means the same thing. It says that the data follows a uniform distribution. It just means that we're expecting the data to be equally distributed across the 7 days. Okay, so this will be a way of you being able to write the null hypothesis. Then, of course, the alternative hypothesis is that the data does not follow a uniform distribution, which means that the birthdays will not be equally distributed across the 7 days. Okay. Of course, there are many ways to write the null and the alternative hypothesis, but this would be a very neat way of writing the hypothesis without actually specifically talking about birthdays. And this would obviously be accepted in the IB as well, again, depending on the context that's given to you. So we're going to find what's the degree of freedom. And I mentioned before the degrees of freedom, which I'm going to talk about it now. Now, since we have 7 sets of data, and we know that degrees of freedom is looking at how many independent pieces of information you have. So in this case, we have 7 pieces of information. Now, again, if we have 6 pieces of information, do I necessarily need to tell you the data for the 7th one? So let's say I've given you the numbers from Sunday to Friday. Do I need to give you the data for Saturday? You don't need to, because all you need to do is just take the total number of students and you subtract the data that's being given to you from Sunday to Friday, and automatically you should be able to find the data for Saturday. So since we have 7 pieces of information, and to find the degrees of freedom, we'll take n minus 1. So it's quite different from the chi-square test of independence. In this case, for a chi-square goodness of fit test, we always take the total number of sets of data and we subtract 1 in this. So we're going to take 7 minus 1. So degrees of freedom is going to be 6. Now, what we're going to do now is we're going to put this all onto the calculator, which is obviously the important part, because if you can get the calculator to get the job done, then we should be able to work out what the chi-square test statistic is, or even using the p-value if we want to. Okay, so because in part C it says that the critical value is given, and they also give you the significance level, so it's really your choice to compare the critical value to the chi-square test statistic, or we could compare the p-value to the significance level. Both would be fine. Okay, now, so what I want you to do now is we're going to use the calculator under L1 and L2. Remember, under stats, when you put the data into L1 and L2, we're going to put the data in L1 to be, again, I'm using the TI-84 calculator. I'll show you shortly how this works. We're going to be putting in, for T1, what you want to do is to put in the data that's given to us, which is the observed frequency. And L2, we're going to put the expected frequency. Okay, this is important, guys. All right, just got to make sure you put the right numbers into the calculator. So the observed data would be these numbers here. That will go into L1. Then the data here is going to go into L2. All right, so let's show you how this works on the calculator. Okay, now so I'll put the data in this case. So this would be 12, this would be 14, this would be 18, 17, 15, 15, 14, and under L2 I'll put the expected frequency, which is going to be 15 for each of it. Fifteen. Okay, so we're going to do the same thing like what we did with the chi-square test of independence. We're going to go to stat, we're going to go to test. Now I will need you to scroll down and you will see this, which is the chi-square golf test. Golf obviously means goodness of fit, so we're going to click that. Okay, so the observed frequency by default will always be L1, expected will be L2. The number you would have to change would be the degrees of freedom, that would be 6. The color, I'll leave it up to you to decide whether you want a different color. Then we're going to calculate this. Okay, there we go. So you're going to have the p-value to be 0.953 if you round off to 3 significant figures, and we have the chi-square test statistic to be 1.60. Okay, so I'm going to use this value and we're going to compare that to the data that we had earlier. So let's look at this. Okay, so what I'll do is it's a bit messy, but I'm just going to clear this up first. Alright, so let's look at part C. Now we do know that the chi-square test statistic that we have was 1.60. The p-value was 0.953. So I'm going to show you how we can compare these both results to what is given to us. So if we compare the p-value to the significance level, which is 0.05, so we know that 0.953 is obviously bigger than 0.05. Okay, so in this case, which means that we fail to reject the null hypothesis because of insufficient evidence, which means that the data follows a uniform distribution. Or you could compare the chi-square test statistic, which is 1.6, and that's less than 0.95, which is less than 12.592. So it's the same conclusion that we have here. Fail to reject the null hypothesis. Data follows a normal distribution. Does this kind of make sense? It's quite similar, isn't it, to the chi-square test of independence, but we're not really testing for independence in this case. We're looking at whether the observed frequency would be, would it actually tally with the expected frequency? And again, the null hypothesis was created in this question because we're looking at whether is it likely for each of the day to have the equal number of birthdays. So like I say, of course, you may even consider writing the null hypothesis to have equal birthdays on every day, but it's just that I would prefer to use a uniform distribution because that can be applied to all different contexts given to you in the question. Okay, so I hope this kind of makes sense of what the goodness of fit test actually does. And going to be looking at maybe another example here. So this question looks very, very similar to what I've just done. Again, it's about birthdays, so I'm not going to go through this question. Maybe let's look at this one. All right. And see if this works out for you guys. Okay, now let's look at this question first. I think the biggest issue with this questions is about how to formulate the null and the alternative hypothesis. So let's look at this example and see if this makes sense to you. All right, so you really got to read the question before we formulate the hypothesis. Okay, so it says the table shows the grade received by university students taking a second-year computer science course. In the following semester, a new coordinator is appointed for the course. The new coordinator is concerned by the high number of high distinction and the distinctions awarded, and wants to determine if the cost should be adjusted. Now, it is considered usual if 5% receive a high distinction, 10% receive a distinction, 15% receive a credit, 40% receive a pass, and the remaining 30% receive a fail. So it says calculate, use a goodness of fit test to determine whether the cost should be adjusted with a 5% level of significance. Now, so what we have here is the observed frequency. Okay, and this would be the expected frequency. Okay, so what we need to do now is we need to do a bit of a calculation here, because we do need to find out how many people are expected to get high distinction, how many people are expected to get 10% distinction, and so on. Okay, but we're not given that data. We're only given that in terms of a percentage in this case. Now, so let's try to formulate the hypothesis first before we can actually talk about how many people should be getting a high distinction and so on. Okay, so watch me and look at how I would write the null hypothesis for this particular case, which is quite different because we're not looking at a uniform distribution, because the percentage of students getting a high distinction and other grades will be quite different in this case. So what I'll do is the null hypothesis, because we're looking at the expected frequency to be part of the null hypothesis formulation in this case. So we do know that for people who are getting high distinction, okay, maybe I should put this, the probability of getting high distinction would be 0.05. Okay, and I'm just going to put down all the probabilities of those getting different grades. Distinction, it's going to be 0.1. Probability of credit would be 0.15. So I'm putting all the expected data that's given to us as the null hypothesis, because they're not uniform, so we don't really have a choice. So we got to write down all the probabilities that's being given to us as the null hypothesis, 0.4, and the probability of getting a fail would be about 0.3. Now, of course, the alternative hypothesis is that if you don't get these numbers, then obviously that will be considered unusual, isn't it? So we have to say that the probability of getting high distinction, so I'll tell you what, rather than writing this not equal to 0.05 and so on, we know that as long one of these numbers are not the same, then this is not considered as a usual usual grades for this particular for this course. So what I can do is, rather than just writing that the probability will not be the same, we can say that at least one of these probabilities will not be the same. So in other words, I could say that high distinction is not 0.05 and so on. Okay, so which means that we probably could look at this not to be the same, 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 and this not to be the same. Okay, so I think as long as we say that at least one of the probabilities will not be the same, I think that would be good for an alternative hypothesis for this case. Now, so this is what we will do when it comes to formulating the hypothesis for this one. So now we want to find out what is the expected frequency, because we are given these numbers for observed frequency, but we don't really have the expected frequency. So this is a bit annoying. You will have to kind of work out these numbers on your own, right? And I'll show you how we can do that. So let me just clear this up first. And let's look at the expected frequencies. It's not a difficult process, but it's just a bit annoying because the numbers are not given to you. So let's look at high distinction first. Now we know that it's considered usual if 5% receive a high distinction. So we're looking at basically we have 151 students in total. So if I take 151 times 0.05, that's going to give you approximately about 7.55. Okay, we don't want to round this to the nearest whole number. We want to keep the level of accuracy. So I'm going to keep this 7.55 as my expected frequency. I know you can't really have 0.55 of a student, but this is really needed when we put this onto the calculator to ensure a level of degree of accuracy for that as well. Okay, so we do that the same thing for distinction. So that would be 151 times 0.1 because we have 10% who receive a distinction. So that's about approximately about 15.1. Then we do the same thing for credit. We take 151 times 0.15. That'll be 22.65. Then we do the same thing for pass, which is 151 times 0.4, which is 60.4. Then if we have a fail, we take 151 times 0.3, that's 30%. So that's 0.3. That'll be about 45.3. Okay, now I got all these numbers here. Perfect. It's time for us to use the calculator. So remember, L1 would be observed. L2 would be expected. All right, so let's put all these numbers onto the calculator. Okay, so back to the calculator. We're going to go to stat, edit. Let's delete all the data first. Okay, then we're going to delete L1 as well. Okay, so let's put the observed frequency, which is what was being given to us in that table. So that was like 16, 21, 21, 59, and 34. Okay. Then we're going to go to L2. And we're going to put in the data that we just calculated earlier, which is 7.55, 15.1, 22.65, 60.4, and about 45.3. Okay, so we try to keep a certain level of accuracy for these numbers. Then we do the same thing again. We go to stat, we go to test, then we're going to go to the golf test here. We're going to press enter. Then we're going to calculate right here as well. So in this case, we have L1 and L2 in this case. And because we have 5 sets of data earlier, so the degrees of freedom will be 5 minus 1, so it should be 4. Oops, sorry. Let's try to do this again. Golf test. Oh my god. That's the price for not paying for the paid version for that. And we got the apps for this. Okay. And oops. Lots of bloopers. Sorry about that. Okay, let's click on that again. So this should be, let's delete this. This should be a 4. Because we have 5 sets of data, subtract 1, that should give me a 4. So we're going to calculate this. And there we go. Scroll down. So let's look at this. This doesn't look too right. And oh, for some reason I didn't put 45.3 here. Okay, so let's go back to stat again, test. Let's go back to the golf test. Degrees of freedom is 4. Yep, everything should look fine. And there we go. Let's scroll up. So we have the chi-square, the p-value to be 0.0528. Okay, so obviously this would be the p-value. But in this case, since the critical value is not given, then looking at the chi-square test is probably not going to be very helpful. So we'll be looking at 0.00529 as the p-value. Okay, so let's get back to that. So since the p-value is 0.0529 and that is bigger than 0.05, which is the level of significance, so in this case we are going to accept the alternative hypothesis, right, which is basically 0.0529. No, sorry, I think I wrote the wrong number. What's this first? It was 0.00529. Okay, so the p-value, oops. Let's look at this one. So p-value will be 0.00529. So since 0.00529 is less than 0.05, so we're going to reject the null hypothesis, which means that we will accept the alternative hypothesis, which means that should you adjust the cost? Of course you should adjust the cost. Okay. Because that's me, we're assuming that one of the probabilities will not be the same as what was meant to be considered usual, because we are accepting the alternative hypothesis. So in this case, the cost should be adjusted. All right, I hope this gives you a little understanding of what the goodness of fit test. Generally, it looks very much the same, but in summary, what we're trying to do is we're trying to compare the observed frequency with the expected frequency, and we formulate the hypothesis depending on the context of the question. So formulating the hypothesis might be quite different. Again, like I said, if the context is given to you in a different way, then you would have to adjust formulating your hypothesis as well. Then the rest of the data, which is the observed and the expected frequency, can be put onto the calculator to either calculate the critical, the chi-square test statistic or the p-value, and we can make comparisons to the significance level or the critical value, depending on what is given to you as well. So generally, it works very similar to the chi-square test of independence. All right. Hopefully, this gives you some insight into what a goodness of fit test will look like. And in another video I'll show you how this can be applied to the normal and the binomial distributions as well. But I hope this gives you an insight into how this works with the calculator as well. So I hope you like this video. Again, as always, subscribe to my channel, like the video, and I'll see you guys very soon.